Hi everybody, welcome to Calculus 1 review. Question 1. Determine all the critical points for the function. So to find critical points of a function, we need to find derivative, and after that we let derivative equal to 0 or derivative does not exist. But whatever the points we find must be in the domain. Meaning when we substitute back into the function, the function is defined at those points. Alright, so of course first we need to find the derivative. Give us 3x squared minus 18x. Right, and we just need the derivative equal to 0. Derivative does not exist. So derivative equal to 0, 3x squared minus 18x equal to 0. So we factor out 3x, x minus 6 equal to 0. So 3x equal to 0 or x minus 6 equal to 0. So that gives us x equal to 0 or x equal to 6. Now, derivative does not exist. This is a polynomial function, so that it is defined everywhere. So we're not going to find anything here because derivative is defined everywhere. Right. One thing we need to watch out for is that must be in the domain. So we'll make sure that when we're going to put 0 in for x, it is defined, and when we put 6 in for x, it is also defined. So just do this quickly. If we put 0 for x, so that equal to 4, which is defined, and put 6 in for x, I just say 6 store to x, and then evaluate the function. That's negative 104. So those are defined values. So those points are critical points. Alright. Next we have for x squared minus 128 times square root of x. This will take a little more work, so, and the problem is longer, so try to write smaller. Right, before we find the derivative, we write square root of x as 1/2 x to the 1/2, so we use power rule for that. So for x squared minus 128 x to the 1/2. Right, now we can take the derivative. Try to write small. Right, power rule, take out the 2, 4 times 2 is 8 x minus 128 x to the 1/2. I will take down the 1/2, and original power 1/2 minus 1. 1/2 minus 1 is minus 1/2, right? Ax 128 times 1/2 is 64. X to the negative 1/2. Negative exponent, if we move to the bottom, it becomes positive. Right. Now we have fraction. When we solve for derivative equal to 0 does not exist, it is better if we have one big fraction. You see that in a minute. So to get one big fraction, what we do, is try to get the denominator of x to the 1/2. So I will multiply top and bottom. Right. Now multiply to the top x times x to the 1/2. So we can say it x to the first and x to the 1/2. When we multiply them, add the exponent 1 plus 1/2 is 3/2. So have ax to the 3/2 of x to the 1/2 minus 64 x to the 1/2. Now we have x to the 1/2 at the bottom. Common denominator. On the top we have ax to the 3/2 minus 64. Right. So that is the derivative. One big fraction like that. So for derivative equal to 0 for fraction, that is the same as saying the top equal to 0 and when it does not exist, it's the same thing as saying the bottom equal to 0. Divided by 0 is undefined. Right? So the top is equal to 0. Move to 64 and divide by 8. Have x to the 3/2. Move 64 divided by 8. Give us 8. Now x to the 3/2, if we rewrite the power be on the top, or the top is power, the bottom is index of radical. So we have square root of x cubed is 8. Square both sides. That gives us x cubed equal to 8 square, which is 64. And then we take cube root on both sides to cancel the cube. When we take the cube root on both sides, we do not put plus or minus. If it is an even root, square root, fourth root, there will be plus or minus. So that gives us x, and cube root of 64 is 4. So we have x equal to 4. Next, derivative does not exist where the bottom equal to 0. X to the 1/2 equal to 0. That is square root of x equal to 0, and we square both sides. So we have x equal to 0. Right. So if x equal to 0 and x equal to 4. And also we check if we put in 0, we're going to have 0. And when we put in 4, 4 is down to x. And then we have 4x squared minus 128 square root of x. And that's negative 122. Yeah, so both of them are defined values. So x equal to 0 and x equal to 4 are critical points. Right. So that is where we find critical points. We let derivative equal to 0 or does not exist, but make sure that it is in the domain of the function. If the derivative is a fraction, or if anything that have a fraction in it, try to combine that into one big fraction. So we let the top equal to 0 for it to be 0, and let the bottom equal to 0, so it will be undefined. Right. Next we'll find absolute extremum, meaning absolute maximum or absolute minimum. In order to do that, we have a closed interval and a function on that closed interval. So this the way we find it is we find the critical points in that interval, and then we test them on the points along with the boundary. So the first step is find the critical points. On this interval, critical points in the interval -2 and 5. So we check the derivative. Check that 3 times 1/3 is 1, so just have x squared. Move down, that will give us 4x and plus 3, and then we let it equal to 0 the analysis. We don't have fraction here, so that's all we have. So x squared minus 4x plus 3 equal to 0. So we factor out x minus 1, x minus 3. Right? Right, so we have x minus 1 equal to 0, x minus 3 equal to 0. So we have x equal to 1, x equal to 3, right? And then the derivative data analysis, there will be none once again, because it is a polynomial. Derivative is a polynomial which is defined everywhere, right? Now, we do need to make sure that it is actually defined. So we don't need to do that because this we have the domain. And so in the domain of -2 and 5, we have both of those points. If we have like -3, -3 will not be in this interval. So, but in this case we have x equal to 1 and x equal to 3. Now, put all of that together in the table. That is the first step. The second step is just put everything in the table. And since we asked for the maximum values, in this case minimum values of original function, so we will use the table using the original function. So we'll make a table. Right, original function 1/3 x to the 1 x cubed minus 2x squared plus 3x minus 4. We are given the interval of -2 and 4, -2 and 5. The points in between 1 and 3. Right. So since all of those are integers, it would be better or most direct we just enter the function and look up the table values. X cubed minus 2x squared plus 3x minus 4, and we just go to the table and look for the values. -2 is -62/3, 1, -1, I'm sorry, this is 1, -8/3, and 3 is -4, and then 5 is 8/3. So this problem asking for the minimum, but if we want the maximum, it will be 5, and so this is the minimum. So the answer will be so the absolute minimum equal to negative 62/3 at x equal to -2. Right, so that's what we have. Right, same thing. Find the extreme values of the following function, right? 5x to 2/3 from -27 to 1. Right, so find the critical points in the interval. So we just said, first step, find critical point in the interval of -27 to 1, right? So that is a function, so we'll take derivative and make it equal to 0. The data exists. The 2/3 coming down, original power -1. So multiply on the top, we have 10/3 x to the -1/3. Negative exponent move to the bottom, become positive. Right. So that is the derivative. So we make it equal to 0. They don't exist. We do have a fraction here, so we let the top equal to 0. Or the bottom equal to 0 when it does not exist. Right, the top equal to 0, we have 10 equal to 0, which is not possible, so there's nothing here. The bottom equal to 0, 3x to the 1/3 equal to 0, so x to the 1/3 equal to 0. X to the 1/3 is cube root, and then cube both sides, we have x equal to 0. Yeah. So make sure that it is in the domain, and so this is 0 belong to the domain. Yes, so x equal to 0 is in the domain. Next, we will just put everything in the table of the original function. So we have a table. Original function. We have the boundary of -27 and 1. In between, there's a critical point, x equal to 0. So we just put everything in the table. Sorry. Please say 5x to the 2/3. There are a lot of different ways to do this. We can store the number into x and evaluate. I do this different every time, so you see there's a lot of different ways to do this. So enter everything in y1 if you want to say y variable y1 and evaluate -27. That's work. Or you can also hit the alpha and trace. There's a y1, hit enter. Now we will evaluate at -27. Give us 45. Of course, when we put in 0, we have 0, but yeah, just to confirm it, and put 1 in there, that would be 1, so it will be just 5. And so this case, as for the absolute extreme values. So we have the absolute max and absolute mean. Yeah, notice we have to use the original function. So the conclusion, absolute max equal to 45 at x equal to negative 27, and absolute mean equal to 0 when x equal to 0. Right, this one we want absolute extreme value, so absolute max or absolute mean. Alright, next, this two problem, we have the same concept. The largest interval where the function is changing as requested, we want decreasing. So whether it's increasing or decreasing, we need to find derivative. When derivative is positive, the function is increasing. When derivative is negative, the function is decreasing. So we will find the derivative. The derivative of this, of course, we can just use the quotient rule. We can also use the chain rule. If we rewrite x squared plus 1 to negative 1, and we can use the chain rule. However, I prefer to use the quotient rule, because when we use the quotient rule, we end up with a fraction, so we can just say the top equal to 0 or the bottom equal to 0. Right? Right. So here, the quotient rule, u equal to 1, the top, v, the bottom, v is x squared plus 1. Now derivative of u is 0, derivative of v is 2x, and then derivative, this is a fraction, or I mean the quotient, so the quotient rule u prime v minus u v prime over v squared right. Let's just simplify that. 0 times anything 0, so that's negative 2x, and x squared plus 1. I will not multiply out the denominator. Usually when we do the quotient rule, we don't multiply it out. Right, now derivative equal to 0, meaning the top is 0, derivative does not exist, the bottom not equal to 0, right? So if negative 2x equal to 0, so divide by negative 2, so x equal to 0, the bottom equal to 0. Take the square root on both sides, we have x squared plus 1 equal to 0. Move the negative 1 over and take the square root on both sides again. But remember, every time we check the square root, there's a plus or minus. And we have a negative inside square root, so this is imaginary. So in that case, it's undefined, so there's no real numbers. So the only number we have is 0. Right, and then of course we also put 0 in here. We have 1, but we do not need to do this, because we want an open interval. So the answer would be an open interval, not a point. Even 0, when we put in the function, it is defined. Right. Now, this we want in decreasing, or whether it is increasing or decreasing. We're going to put everything in the sign chart. And the sign chart using derivative, because we need the sign of the derivative. Where derivative is positive, it is increasing. Where derivative is negative, it is decreasing. So we'll make a sign chart. So we have x. X will take the values from negative infinity to infinity. And then here we put the derivative. Negative 2x. X squared plus 1 squared. So whenever derivative is positive, it is increasing. Negative, it is decreasing. We have one point here, which is 0. That where derivative equal to 0. Right? Then we can use the test point. Right, to put negative 1 in here, the top is positive. The bottom is always positive because of the square, x squared plus 1 squared. So, and then put 1 in here, that will be negative. Right? So that is the derivative. But in terms of function, positive is increasing, negative is decreasing. And it is because x equal to 0 belongs to the domain of the function. So we have the maximum here. But the question did not ask us that. The question asks us where the function is decreasing. So we say from 0 to infinity. It is an open interval, so it is an open interval. All right. So wherever the function is increasing or decreasing, we will use the sign chart of the derivative. That we can determine if it's positive, the derivative is positive, the function is increasing. If it's negative, the function is decreasing. Right. Similarly, we have this example: x to the 4th minus ax 18x squared plus 81. Just polynomial, so derivative will be easy. For x cubed minus 36x. Will that equal to 0 or does not exist? We don't have fraction here, so just that. So factor out, we have 4x in common. Then x squared minus 9. For x equal to 0, x squared minus 9 equal to 0. So x equal to 0, x squared equal to 9. Take the square root on both sides. X equal to plus or minus square root of 9. So we have x equal to 0, x equal to 3, x equal to negative 3. Derivative does not exist. This is a polynomial, so it is defined everywhere. Right? And then the sign chart. Once again, we do not need to put this point back into here, the original function, because one, the original function is polynomial, so it is defined everywhere. We don't need to do that. Second, we don't have to do that because the question asks for an open interval, so we do not know what happened at the point. We just need to know what happened in between those points. So if we ask for the local maximum or local minimum, then we need to evaluate at this point. Just make sure we have the values. But we only need to find where the function is increasing, so the sign chart will be enough. And the sign chart using the derivative. Derivative is positive, increasing, negative is decreasing. Right. X, and then derivative for x cubed minus 36x. Right, here we just have the number line. 0, 3, negative 3, right? So just put them in increasing order, negative 3, 0, and 3. Right, when we have those values, the derivative equal to 0 at those values. If it does not exist, I will write did not exist. Right, and then pick the test point. The test point will be in between the interval. I choose negative 4, negative 2, or positive 1, 4. Right, put everything into the derivative. Right, so let's put that in the function. So I'm going to put derivative and then we need to evaluate at this point. So those are integers we can just look up in the table, right? Or we can also do this: alpha, trace, and y1, and then we just evaluate at those points, and then so on. If we want at all of those points, open curly bracket, negative 4, comma, negative 2, comma, 1, comma, 4, close it. So we evaluate at all those points, and we have negative, positive, negative, positive, negative, positive, negative, positive, decreasing, increasing, decreasing, and increasing. So we have a local minimum, local maximum, local minimum, but that the question did not ask us that. The question asked where the function is increasing. So we just say from here to here and from here to here. Or from 3 to infinity. Right, so that is where we find the interval where the function is increasing or decreasing. Increasing is where the derivative is positive. Decreasing is where the function, where the derivative is negative. Of course, from there we can find local max and local mean. Right, which is what we have here. Find the local extrema of the function. So we again take derivative equal to 0 does not exist, and then in this case we ask for the local extrema, meaning the local minimum, local maximum. It is a point, so we do need the function to be defined. Right, so that's the game plan. But first take derivative for x cubed minus 4x. That's it. Right, equal to 0 does not exist. So for x cubed minus 4x equal to 0. So for x, x squared minus 1 equal to 0. So we have x for x equal to 0, x squared minus 1 equal to 0. So if x equal to 0, x squared equal to 1. Take the square root on both sides. Don't forget there's a plus or minus. So if x equal to 1 and x equal to negative 1. So we have x equal to 0, x equal to 1, and x equal to negative 1. We find the local maximum, local minimum. So those are the points. If we want to find the points, make sure there's the function define at those points. So I'm going ahead and evaluate. F of 0, put 0 in for x. That is negative 9. If we put negative 1 in for x, x to the 4 minus 2x squared minus 9. Alright, evaluate at negative 1. We have negative 10. Evaluate at 1. We have 10. Or just go to the table. Right. Negative 1. We have negative 10 and 1. Also have negative 10. Right. So that is the original function. We make sure that the function is defined at those points. So those are critical points. Besides, when we look for local extremum, local maximum, local mean, so we find the local extreme points, and if we find points, the points belong to the function. The points belongs to the graph of the function, so that's why it have to be defined. Right? If it's undefined, it cannot be the maximum or minimum at the point that's undefined. So see, we look for local maximum point, local minimum point. The point have to be defined, so that's why we need to check, and all of them are defined. This one for the local max or local mean, so we don't put a table. We just use a sign chart. Right. Right, derivative for x cubed minus 4x. Right, and then negative infinity, infinity. We have 0, negative 1, and 1. Those are critical points. All of those where the function equal to 0. Right, test point. Negative 2, negative 0.5, 0.5, and then 3 or 2, doesn't matter. Right, so now notice that this is the sign chart for the derivative, because we want to find the local max or local mean. Of course, if we know the function increasing or decreasing like that, we can tell it is the maximum or the minimum based on from the sign chart. So increasing or decreasing give us a local max and local mean, and increasing, decreasing associated to the sign of the derivative. Right, so the derivative, make sure we put the derivative, not the function, and then we evaluate at this point. Since these are not integers, so we don't have that on the table. We can just get second trace, then values, like that. There's a lot of different ways to do this. I do a lot of different ways too. So negative 2 is negative 24, negative 0.5 is positive, 0.5 is negative. There are a lot of different ways to do this. 96. Of course, you can just say alpha trace and y1 evaluate at whatever the point you want. Right. So decreasing, increasing, decreasing, and increasing. So of course here we have the local max, local mean, local max, local mean. So local mean at negative 1 and 1. And here's the local max. Right, so we said local mean equal to, but we know it's going to be at negative 1. When x equal to negative 1, y equal to negative 10. Right, and then local mean at x equal to 1, also negative 10. Yeah, so that's not only we check the values to make sure the function is defined because we're looking for the points, we also find the values, so the answer will be there later. So local max will be at x equal to 0, and this is negative 9. Right, so that is what the first derivative tells us: increasing or decreasing. Positive is increasing, negative is decreasing, and from decreasing and decreasing or increasing, we can find local max, local mean. Right, next we have concave up or concave down. Concave up or concave down is dealing with the second derivative. So we pretty much do the same thing with the sign chart and all, but this time we use the second derivative because this is dealing with concave up or concave down. Right, so second derivative. Take derivative, give us 3x squared minus 6x plus 2. And then take the second derivative, 6x minus 6. That's it. Equal to 0, does not exist. Otherwise, there's none here. Also, polynomial is defined everywhere, so we don't have anything here. Right, 6x minus 6 equal to 0, so x equal to 6 divided by 6, so x equal to 1. Of course, we can put 1 back in here, but this we ask for the interval, so we don't need to find the point. So if we ask to find the inflection point, maximum point or minimum point, we need the original function because those points belong to the graph of the function. So we need the original function. Of course, if we want to, we just put 1 in here, it is defined, no big deal. What we need is find where the function is concave up and where it's concave down. So that is the sign chart for the second derivative. Right, so make a sign chart. This is the second derivative. right? Actually there's only one point here where the derivative, second derivative equal to 0, so we only have one point, right? Test point to 0 and 2, and I put in here, put in 0, we have -6, put in 2, 12 minus 6 is positive, so that is the sign of the second derivative. If it's negative, it's concave down, positive concave up, and of course that's how we memorize it. So concave down from -infinity to 1, and concave up from 1 to infinity. Next, find the largest open interval where the function is concave up. So we're going to take the second derivative of this. Of course, we can use the quotient rule, but it may get a little bit complicated after that. Okay. There's a lot of ways to do that, so I'm just going to say it. X plus 1 move to the top, x plus 2 move to the top. I just want to review the chain rule, that's all. Now we take the first derivative, we move down to -1, and then original power to -2, and then derivative of whatever inside the parentheses, right? So something to -1, take -1 down, original power reduced by 1, and then we take derivative of the parentheses. It just happened to be x plus 2, right? So that's -3 x plus 2 to -2, and derivative of x plus 2 is 1. So -3 x plus 2 to -2. Now we check the second derivative, right? -3, and take down the power, original power -1, and then derivative of the parentheses. So that gives us 6 x plus 2, and derivative of x plus 2 is 1. So we have -6 x plus 2 to -3. Right, so that is the derivative. Of course, if we move that to the bottom, -6 x plus 2 cube. Of course, you can also use the chain rule. I mean, the quotient rule. Right. Second derivative equal to 0. In this case, we have the fraction, so that means the top is equal to 0. Or does not exist. That's where the bottom equal to 0. Right. The sign chart will be here. Right. Top -6 equal to 0. That doesn't give us anything. The bottom, something cube equal to 0, so that means it by itself is equal to 0. So take the cube root on both sides, move the -2, move 2 to the other side, or subtract 2 on both sides. We have x equal to -2. Right. Just note that if we put -2 in here, it is undefined. So it is not a critical point. It cannot be the maximum or minimum, or cannot be an inflection point, because the point does not exist. It cannot belong to the graph. Right. But we're not asking to find inflection points or maximum or minimum. We only ask for the interval where the function is concave up. I'll make a sign chart using the second derivative. Right, second derivative we only have one point, and negative 2 is where the function does not exist. Right, test point to 0, and here we choose sorry 0 is over here, 0, and then sorry zero over here, and negative 3 over here. Right. Right, second derivative, I can just put this as second derivative. Right, and let's go to table. Negative 3 is positive and negative. So concave up and down. So this is concave up. So the answer will be from negative infinity to negative 2. Right. So once again, second derivative will tell us whether the function is concave up or concave down. If, by the way, here we have concavity changing from negative to positive, so there is an inflection point here. The question did not ask us that, but the inflection point will be there. So the second derivative tells us concave up, concave down. From there we can determine if it is an inflection point. It cannot be an inflection point here because the function is undefined. Right, and the first derivative tells us increasing or decreasing, and from there we can find local max or local mean. Right, next we have the second derivative test. Right, so we test for the second derivative. So of course in that case we need to have the second derivative, obviously, for the second derivative test. So in order to do that, first of all, we need to have the derivative, and the derivative must be defined. If the derivative defined, it is the critical point, and then we can go from there. So to summarize the second derivative test, first we do need the derivative equal to 0. And they will say, what happened with the case when it does not exist? Well, if the derivative does not exist, there is no second derivative. So we cannot use second derivative test. So if we want to use second derivative test, we need the derivative to be defined. And in this case, equal to 0, so it's guaranteed that it is the critical point. And then we use the second derivative test. It's easy, intuitively. I don't have to write everything, but if it's positive, remember the smiley face, concave up, have to be local mean. If it's negative, the sad face, concave down, and that is the local max. Or also, I mean, it's only local max or local mean. And if it's equal to 0, it's inconclusive. So that is the second derivative test. This is local max and local mean. So we are given the pawn, so just going to test. We don't have to find the pawn. We're just going to test x equal to 0 and x equal to 2. X equal to 2 for that function, x equal to 0 for this function. Right, so simple enough. First we do need derivative, and then the second derivative. Derivative is 6x squared minus 6x minus 12. Right, now we test at x equal to 2. 6 2 square minus 6 times 2 minus 12. Right, 24 minus 12, so that is 0. And so check, it is a critical point. If it's not equal to 0, it is not a critical point, and so we're not going to go to the second derivative test. It have to be critical points before we go to the second derivative. Of course, that gives us 12x minus 6. And now we test at x equal to 2. The second derivative, 12 times 2 minus 6. 24 minus 6 is 18. It's positive. So the smiley face, concave up, local mean. So we say local mean at x equal to 2. If we want to find the values, it's easy. Just going to put 2 back in here. Just need to evaluate at 2, so I just store that into x and evaluate. It's -2. Right, simple enough. Right, so for this one, first we'll take the derivative. 12x cubed minus 12x squared minus 24x evaluate x equal to 0. Derivative at 0, 12 0 cubed minus 12 times 0 square minus 24 times 0. So that check derivative equal to 0, so it is a critical point. That means we can go further. Right, now we go to second derivative. Uh, 36 x squared minus 24 x minus 24. Now evaluate x equal to 0. Second derivative at 0. 36 0 square 24 0 minus 24. Of course that's 0. We have -24, which is less than 0. So negative, the sad face, concave down, and so there's a local max. So we say local max equal to at x equal to 0. Of course put 0 in here, so there's on x at 0. This is just positive 24. Right, So that is the second derivative test, this part. Next, show the problem. A piece of molding of 188 centimeter long is to be cut to form a rectangular picture frame. What dimension will enclose the largest area? Right. So we have a piece of molding. And say it will cut into 4 equal pieces. Not 4 equal pieces, sorry. It's just going to cut. Right. So I have a piece of molding 188 centimeter long and cut and to form a rectangle. See. Okay. So make that into a rectangle. Let's say there's a x, y, x, y, so we can make it into a rectangle. Right. And then what will enclose the largest area? Of course, the area of rectangle. Length times width. Alright, so we try to maximize x times y. But in here we will say that x plus y plus x plus y, or 2x plus 2y have to be equal to 188. Right, from here, if we divide both sides by 2, divide everything by 2, I will have x plus y equal to 188 divided by 2, so that is 94. Or we can solve for y. So that's what we have. Now if we substitute this into y, so the function we try to maximize, it is the largest area, so maximize x times 94 minus x will be 94x minus x squared. Right, so that is the function we're trying to maximize. When we do that, we also need to have the limit as well. So notice that the measurement for x and y must be greater than or equal to 0, right? Because the measurement cannot be negative, right? After that, we have x greater than 0 and y is 94 minus x greater than or equal to 0. Move the 94 over. And then divide by -1 on both sides. Every time we divide by the negative number, reverse inequality. So we have x greater than or equal to 0 and x less than or equal to 94. So indeed we have the boundary. So we try to find the maximum of that on this interval. So I will usually say the work problem become the math problem. And so the problem is try to maximize this. (94x minus x squared) on the interval of 0 and 94. Alright. Now the problem will simplify to something like this. Try to find the maximum or minimum of a function on a closed interval. Right. So find a critical point on the interval. So take derivative 94 minus 2x and then equal to 0. They not exist. We give us nothing. Subtract the 94 on both sides. Divide by -2. And 47 belongs to the interval, so that's good. And indeed it is. Right, next we find the absolute maximum in this case. So we will use the table and compare every critical points along with the boundary using original function. We have the boundary of 0 and 94 and original function 94x minus x squared and the critical point in the middle 47. Right. Actually it's simple enough, but just want to review. There's a lot of different ways to do this. So enter that in y1, and now we have y1 evaluate at those points 0, 90, 47, 94. So 0, 0, 2209, and of course this has to be maximum. So the question is, what dimension will enclose the largest area? So we know the maximum occur at x. X equal to 47. If x equal to 47, 94 minus 47 is also 47. So the maximum area will be where the dimension is 47 by 47. Right. Now we shift gear to something else. Use differentials to approximate the quantity to 4 decimal places. Right. So approximation. Using the linear function, just like the equation of tangent line. So I will say it. Equation of the tangent line. Let me write that. That is equation of a tangent line. If I do that correctly, derivative and the values of the function evaluate at a. The equation of tangent line and linear approximation saying the values of the curve is approximately equal to the equation of a tangent line. Right, so we have a curve. If we have the tangent line, then when x close to a, the values on the curve is close to the values on the line. Right, so pretty much we have that. So in this case, we need to identify what is x, what is a, and what is the function. Well, the easiest one to determine is whatever number we see in the problem, that's going to be x. So we let x equal to 145, then that becomes f of x is square root of x, or x to the 1/2. Right, so that whatever number we see in the problem is going to be x. Next, we're going to choose a. A is the number that is close to x but evaluate nicely without a calculator. So we're going to choose a number that is close to 145 and square root come out nice and even. Well, we know square root of 144 is 12, so we choose 144 because square root of 144 is equal to 12 exactly. So square root of 145 is 12 point something. Right, now that's what we need to evaluate. Right, so we need the values of the function. We need the derivative at the point A. Right, so that should be easy. The function is square root of x, or x to the 1/2. Now we evaluate at A. F of 144 or square root of 144 equal to 12. Now we check derivative. Derivative is 1/2 x to the negative 1/2. Negative 1/2 I move to the bottom, become positive, and that is square root. Right, and then evaluate at 144. Derivative at 144, 1 over 2 square root of 144, which is 12. 1 over 2 times 12 is 1 over 24. Right, so we have everything. Now let's go put back into the linear approximation. Just the equation of a tangent line. Right, derivative we have is 1 over 24 x 145 minus a plus f of a 12. So that is 1 over 24. 145 minus 144, just 1. Right, we need 4 decimal places. So 1 divided by 24 plus 12. So the answer is 12.0417, 4 decimal places. Now if we take square root of 145, it is very close to it. So that is very good approximation. It is a very good approximation because the point is very close. A and x are very close. The point is x is given in the prompt. We cannot choose that. We can only choose a to be close to it. Just like this. Whatever the number is going to be x. So let x equal to negative 0.01. Then the function is sine x. If x replaces to the number, we have sine x. Right, then we choose. We choose whatever values. I come out nicely. Evaluate close to x, but evaluate easily. And of course, we're going to choose 0. To say is equal to 0 because sine of 0 is equal to 0. That come out nicely. Right, now the function is sine of x. Evaluate at 8. Sine of 0 is 0. Next, the derivative of sine is cosine, and at a equal to 0, derivative is cosine of 0 is 1. And we have everything put in linear approximation or equation of a tangent line. Derivative cosine, so it is 1. X negative 0.01 minus a plus f of a sine, so that's 0. Right, so that gives us just negative 0.01. Well, if you need to use the calculator, make sure in the radian mode on this one, for this one. Right, so that is the values. Of course, this is the good approximation because a and x are very close to each other. Right. Next, we have differentials. This one we try to find dy in terms of dx. Pretty much this is what we have to put the answer as. It's very simple, right? We can see that derivative, the notation is dy over dx. Now, kind of like multiply dx on both sides. Dy is equal to derivative times dx. Right, so pretty much we take derivative. Now this requires the chain rule. We have sine of something, right? Derivative of sine of something is cosine, and then derivative of the parentheses. Right, and it just happened 3x squared in the parentheses. So we have cosine of 3x squared, derivative of 3x squared, 6x. Right. Now derivative, the notation, we can say it is dy over dx. And equal to this. I'm going to write the 6x in front, so I don't need the parentheses. Right, and move the dx over. Right, so just different notation for the derivative and move the x over. Now kind of like that. It is exactly equal to dy equal to derivative times dx. But if we don't have dy dx, we have delta y and delta x. So from here we have approximately the change is equal to the derivative. Now we go to delta x and delta y, and it's no longer equal to, but approximately equal to, right? So this is from a spherical balloon is being inflated. Find the approximate change in volume if the radius is increasing from 5.2 to 5.3, right? So we talk about volume. This is a sphere, and the volume of the sphere 4/3 pi r cubed, right? Then we will take derivative. We have 3 pi 3 r square. 2 and 3 cancel out. 4 pi r square. So this is the area, the surface area of the sphere. So is that coincident that when we take the derivative of the volume we get the surface area? The answer is not. There's a reason for that. Anyway, so now let's just change the notation. If we have dv over dr, that will be exactly 4 pi r square. Move the dr over. Right? Now if we don't use dr and dv, we use delta instead, the change will be approximately that 8 the pi, sorry. Right. Now we go from 5.2 to 5.3. So in that case we say r is equal 5.2, and the delta r it go from 5.2 to 5.3. So the new values minus the old values, that gives us the delta. So the new one minus the old one is 0.1. Right? Have everything, we can put it back in here. So 4 pi r square 5.2. If we want to put, we should actually put the unit in it, centimeter. Right? The difference of centimeter is centimeter. So 5.2 centimeter square, delta r 0.1 centimeter. Right? That gives us centimeter cube. 4 pi 5.2 square 0.1 centimeter cube. Right, just do the math there. Just type the number 4 times 5.2 square times 0.1. I just write like that and then stick a pi to it. 10.816 pi centimeter cube. And of course the unit should be centimeter cube because that is the change in volume. So the volume will increase by 10.816 times pi centimeter cube if it increase by that much. Right, the change in volume, so the answer should be the same as the unit for volume, centimeter cube.